Roots of polynomial equations. We're going to start off with the rational root theorem, sometimes called the zero root theorem or the zero theorem. Now, I've never heard it called the zero theorem. I've always heard it called the rational root theorem. But I'm told that some books call it the zero theorem. It says that if we have any polynomial equation, any at all, as long as it has integer coefficients, the following statement is true. If the rational number p over q, written in lowest terms, is a root of that polynomial, then p is a factor of the constant a sub 0. So then the top number has to be a factor of this number, and the bottom number, the q, has to be a factor of the leading coefficient. Now, if you'll just bear with me, I'm going to explain this in better terms for you so that you can take better notes. So this may not be where you want to stop and take your notes, okay? But let me just say it again and see if it kind of starts to make sense. If you know that the rational number written in fraction form, now we know any rational number can be written as a fraction, 2 over 5, 5 over 1, negative 7 over 3. If we know that that fraction, p over q, is a solution or a root, then it has to be true that the top number of that solution has to be a factor of the constant, and the bottom number has to be a factor of the leading coefficient. So here's what that really means. The rational root theorem gives us a tool that we can use to make a list of all of the possible rational zeros or solutions of a polynomial. It just helps us generate a list that we can start with. So it helps you make a list of all of the possible, not all of them will work. Some of them will work, some of them won't, sometimes none of them will work. Of all the possible rational zeros of a function. Not every number in the list will be a solution, but every rational solution or zero must appear somewhere in that list. So we'll pause for a second, let you jot down anything you want, and then I'm going to give you some steps for making that list. So you'll know step by step how to start when you're asked to apply the rational root theorem. So here's how we use the rational root theorem. First, if your polynomial has any fractions in it, get rid of it. Get rid of them. So multiply through by the common denominator. Make sure all of your coefficients are integers. So first, make sure all of your coefficients are integers. Then make a list of all of the factors of the constant term and all of the factors of the leading coefficient. And that list of numbers is equal to the possible rational zeros. So make a list of all of the possible rational zeros by taking the factors of the constant term, listing them out, and dividing them through by the factors of the leading coefficient term. And it'll only work if all of your coefficients are integers, not fractions. So for our first example, we want to list all possible rational roots of the polynomial 1/2 x to the 4th plus 2/3 x to the 3rd plus 3x squared minus 3/2 x plus 3 set equal to 0. So the first thing we need to do so that we can apply the rational root theorem is we need to get all of our coefficients to be integers. So we're going to multiply both sides of this equation through by 6, which is the common denominator of 2, 3, and 2. So on the left side, 6 times 1/2 is 3, x to the 4th. 6 times 2/3 is 4x to the 3rd. 6 times 3 is 18x squared. Negative 3/2 times 6 is negative 9x. And positive 3 times positive 6 is positive 18. And for the right side, 6 times 0 is still 0. So now we have this polynomial in a form equal to 0 where all of its coefficients are integers. And that will allow us to generate a list of possible rational roots. So the possible rational roots include all of the factors of the constant, so all of the factors of 18, which could be plus or minus 1, 2, 3, 6, 9, and 18. So that will comprise our numerators. Positive 1, 2, 3, 6, 9, 18, or negative 1, 2, 3, 6, 9, 18. And then we stack those over all of the factors of the leading coefficient. So all of the factors of 3 will make up our denominator, 1 and 3. Then we need to split that into all of the possibilities. So if we take all of the top numbers and stack them over 1. So 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1, 9 divided by 1, and 18 divided by 1. We have positive and negative 1, 2, 3, 6, 9, and 18. And now we have to go back through. We've divided by the 1, so we're done with it. So we need to go back through and divide all of those by 3. So 1 divided by 3 is 1/3. 2 divided by 3 is 2/3. 6 divided by 3 is 2, but that's already been listed, so we don't have to list it twice. 9 divided by 3 is 3, and that was listed previously as well. And 18 divided by 3 is 6, which has also been listed. So it turns out that those are all of our possibilities. If we distribute the positive and the negative, that gives us 1, negative 1, 2, negative 2, 3, negative 3, 6, negative 6, 9, negative 9, 18, negative 18, 1/3, negative 1/3, 2/3, and negative 2/3. And that is the list of all possible rational roots. Now what that means is that if that polynomial, p to the x up there, if that polynomial has a rational root, it must appear somewhere in that list. And a little later on, we will talk about how to figure out which ones actually are roots or not. And some of you already have realized that we could just find p of each one of those until we find a number that produces a 0. And that would mean that when we divide by it, the remainder is 0, and therefore it would be a solution. So we'll talk about that a little later on. But for now, let's make sure that you've mastered just listing the possibilities, just how to generate them. So let's do one more example on that. Let's list all possible rational roots of the polynomial f of x equals 15x cubed plus 14x squared minus 3x minus 2. Now this problem is a little bit easier simply because it already has all integer coefficients. So if I just take it and set it equal to 0, and I generate a list of all of the possible rational roots by taking the factors of the constant, which in this case is negative 2. So all the factors of negative 2 are plus or minus 1 and 2, and divide it by the factors of the leading coefficient, which in this case is 15. And all of the factors of 15 are 1, 3, 5, and 15. No other numbers will divide into 15. So then we simply split that up. And we see that that equals plus or minus 1 over 1, 1 over 3, 1 over 5, 1 over 15. Then we'll take the 2 and divide it by each of those. 2 over 1, which is just 2. 2 over 3, 2 over 5, and 2 over 15. So those are all of the possibilities for rational roots. If this polynomial has any rational zeros, it has to appear in this list. And if we distribute out the positive and negative, we have plus or minus 1, plus or minus 1/3, plus or minus 1/5, plus or minus 1/15, plus or minus 2, plus or minus 2/3, plus or minus 2/5, and plus or minus 2/15. So let's count them up and see how many possibilities that was. 2, 4, 6, 8, 10, 12, 14, 16. So it has 16 possibilities for rational roots. Not all of them will work. In fact, we know that it can have a maximum of 3 roots, period. And we're not guaranteed that any or all of them are rational. But if there are any rational roots, they have to appear in that list that we've just generated.